Unit 2, Objective 5 and 6 is related rates here in Calc BC. What are related rates? Well, it's a situation that has two or more variables with movement, and we always take the derivative with respect to time. And when you're doing the derivative, since you're doing it with respect to time, it's really it's like implicit differentiation. Okay, so we just need to go ahead and get going on this. So example number 1, a spherical balloon is being inflated at a rate of 27 pi cubic inches per second. Okay, how fast? Now, by the way, fast, they're not asking the rate, so fast is more like speed. It's going to be a positive value, whether the rate is positive or negative. How fast is the radius of the balloon increasing when the radius is 3 inches? Okay. Let's take a look and see what all that they've given us here. How fast is the radius of the balloon increasing when the radius is 3 inches? So we're trying to find the rate of change of the radius, dr dt, and specifically at when the precise moment in time when the radius is 3 inches. Okay, so that's what we're trying to find out. Now, they're talking about a spherical balloon, sphere, you know, so, and notice that they also gave us this value right here, and so that's a volume, inches cubed per second. That's a volume with respect to time. So this is actually dV dt. And they're talking about being inflated, so the volume is getting bigger. So if we're just thinking about the actual rate, that is a positive, because if it's getting bigger, the volume's getting bigger, it's positive. If they were actually letting air out, then it would be a negative dV dt. But positive 27 cubic inches per second. Okay. So do we have a formula that involves volume and radius and the fact that it's a sphere? Well, yes, of course we do. Okay, so we have V is 4/3 pi r cubed. And so we would, if we took the derivative with respect to time, we would be getting a dV dt, and we would also be getting a dr dt. So this is going to work out very nicely. Okay, so I think we're ready to go ahead and start doing some calculus with it now. So as I mentioned, we are going to be taking the derivative with respect to time. Okay, so we get dV dt. And so, by the way, it's very important when we're doing related rates to actually write it dV dt, and don't just write v prime. It's too easy to mess things up. But, now 4/3 pi, that's just a constant. So so 4 pi over 3. I'm just going to bring that out in front. So the constant times whatever the derivative of r cubed is. So the derivative of r cubed is 3r squared times the derivative of the guts with respect to time, so dr dt. Okay, and so obviously, I mean, it's like we try to go ahead and clean things up if we can. So I noticed the 3's reduce, and now we can also, it's also important not to plug in instantaneous values until after you've taken your derivative. Okay, what do I mean by that? For example, we had the radius of 3 inches. So it was very important that we didn't actually plug in the 3 for the r until after we've done calculus with it. So this is an instantaneous value. You don't plug it in to the formula where r is changing until you have an instantaneous equation, and the instantaneous equation is where you have taken the derivative. Okay, but now we can actually start plugging things in. Okay, so we do have dV dt, which is 27 inches cubed per second. Okay, now, as long as you pay attention to your units, you don't need to actually have the units throughout the problem here. In fact, we should be able to predict what our units are for dr dt right now even. So the change of the radius with respect to time. So radius, isn't that a length? And since we're talking about inches here, so isn't it just inches to the first power over seconds? Our final answer is going to be in inches per second. So as long as you just pay attention in the fact that the units are making sense and they're all speaking the same language here to begin with, then you don't need to include the units in the actual work. It does work if you want to do it that way. It's just you don't have to. So 27 equals, okay, so I have 4 pi r squared, so 4 pi, but this is now an instantaneous equation, so we're going to plug in the 3. So 3 squared times dr dt. Okay, now notice the only thing we don't know is the dr dt, and that's what we're actually trying to find out when the radius is 3 inches, and so we plugged in the 3 for the radius. So let's finish it off. And so really we're just dividing here. Dr dt is 27. Now you could go ahead and multiply it out, obviously it's 36 pi, but I'm noticing that the 3 squared is going to go into the 27 because it's 27 over 9 effectively, so it reduces to the 3 over 4 pi. Okay, so dr dt is 3 over 4 pi. Okay, what did we say our units are? Inches per second. Now, some of you like to write the slanty fractions, and I do myself even once in a while, but just be careful, particularly when you have more than one thing in the denominator, particularly. If you write a slanty fraction, if you write 3, 4 pi, where is the pi? Is it in the denominator? Is it in the numerator? It's probably safe, if you're going to write a slanty fraction, you better put parentheses around it so everybody knows where you are indicating the pi actually is. Okay, moving on. Number 2. Oil spills from a tanker, forming a circle whose circumference increases at a rate. Okay, it's increasing, so this is really a positive value. Rate of 40 feet per second. At what rate is the area of the spill changing? Okay, so at what rate is the area of the spill? So we were after dA dt when the circumference is 100 pi feet. Okay, so that's what we want. So ultimately, since we want dA dt, we're going to have an area formula going. Oil spills from a tanker, circumference, distance around a circle. Okay, so circumference, we could do pi times diameter, but usually, really it's like radius. You want to think radius. So circumference is 2 pi times the radius. Okay, let's see. I know we want dA dt. Let's go ahead and start to write. So area of the circle, so area of the circle is pi r squared. And so if I take the derivative of that with respect to time, I do get the dA dt that I'm trying to get. And over here I've got pi times 2r times dr dt. And at this point now, it's like I'm happy because I can see the dA dt, but I'm also sad because I'm going, okay, I don't know the length of the radius. at that particular, because they told us circumference, and I don't know the dr dt either. Well, let's see. We do know that circumference is 2 pi r. Okay, so if we take advantage of that, so 2 pi r equals 100 pi. So radius would be 100 pi over 2 pi, okay, which is 50 feet. Okay, so that answers one question right there. So we know when the circumference is 100 pi, the radius is 50 feet. So I can plug in a 50 feet for my r, but I still don't know my dr dt. Okay, so, well, let's see. At what rate is the area of the spool changing when this is 100 pi feet? Okay, so, I think we need to actually, didn't they give us something else? They also gave us, we're not using the fact that the circumference is increasing at a rate of 40. We haven't used that yet. If they're giving you information and problem, usually it's pertinent, not always. Sometimes it's extra information, but usually it's pertinent. So what is this value they gave us right here? Circumference increases a rate of, isn't that dc dt? Okay, well, since we have dc dt and we have a circumference formula, I think I can see where we're trying to go with this right now. So let's do the circumference, and we're going to take the derivative of that with respect to time. And so we do get dc dt, but that's okay, we were given that value. And then I have 2 pi times dr dt, and that's good because we're trying to find dr dt. So we can plug in the 40 here. So 40 and divide by 2 pi, and that's the dr dt. And so dr dt is 20 over pi feet per second. Okay, and so we're going to take that dr dt and we're going to plug it into the dr dt that we don't know over here. Okay, so now we can actually finish the problem. Okay, so let's see, dA dt is what we're trying to find out. Okay, so dA dt is equal to pi times 2 times the radius. The radius is 50 feet when the circumference is 100 pi feet. So 2 times 50, 100, and dr dt is 20 over pi. And let's see, the pi reduces with the other pi, and so that leaves us with 2,000. Okay, now it's area, and we're in feet, so 2,000 square feet per second. So the rate of change of the area, 2,000 feet squared per second. Wow, pretty amazing. Okay, number 3. A 6-foot tall person is walking at a rate of 4 feet per second away from a street lamp that is 24 feet tall. Okay, We really got to have a sketch of some sort for this. And you know, don't laugh at my sketch, and I'll try not to laugh at your sketches, or we can just all laugh at each other's sketches. Okay, now we're assuming the lamp is actually perpendicular to ground. It's giving off light. It's 24 feet high, and you got a person who's 6 feet tall, and you know, again, don't laugh at my people. Okay, now the person is walking at a rate of 4 feet per second away. So, okay, so person's walking this direction. Now we have to start assigning some variables here. Well, what things are changing? Well, this distance between the person and the base of the lamppost, that's changing. So that needs to have a variable. So I'm going to call that x. And so therefore dx dt. Okay, now he's walking, sorry, person, not necessarily a he. Person is walking away from the street lamp. So is x getting bigger or smaller? X is getting bigger, therefore dx dt is positive 4 feet per second. If the person was walking toward the lamppost, the x would be getting smaller, and that would be a negative 4 feet per second. So it's very important to pay attention to stuff like that. At what rate, part A, at what rate is the length of the person's shadow changing? Where is the shadow? Well, the shadow is out here. Here is the shadow. And so the length of the shadow is changing as the person is walking. So we need to assign a variable to that. Myself, I don't like putting a y on horizontals. I like to save y for verticals. So I'm going to put a z on it. I don't like s's typically either, unless we're dealing with a position function. You can, you know, but I like doing the z. So we're after at what rate is the length of the person's shadow changing? So we want dz dt. Now it didn't give a precise moment in time of something happening, so I wonder what's going on with that. Maybe it doesn't really matter what time it's changing. Okay, so we're looking for an equation that works here, and something that does come up, and we just have to be ready for it. We have similar triangles here. We have two right triangles, and they share that common angle right there. So by angle, we have similar triangles. And so now there's various ways we can set up the equation, but I'm going to do 24 is to the big, the bottom of the big triangle, which is x plus z. 24 is to x plus z as 6 is to z. Okay. There it is. We've got dx dt, we want dz dt. Now, sometimes it's really nice to go ahead and do some algebra cleanup before you start throwing the calculus around. So let's just clean it up here a bit. We got 24z equals 6x plus 6z. And so 18z equals 6x. So 3z equals x. That looks a lot nicer. Let's take the derivative of that with respect to time. And so we have 3 dz dt equals dx dt. Oh, that's a lot nicer. Okay, we know dx dt. We want dz dt. So dz dt is the dx dt, which is positive 4, divided by the 3. See that it didn't really matter at what time this thing is happening, since the person is moving at a constant rate of speed here. 4/3, now that's a length, so it's just the distance unit, which is feet, per the time unit, second. Okay, part B. Part B, how fast is the tip of the person's shadow changing? Well, first off, where is the tip of the shadow? Tip of the shadow is right out here. And the tip of the shadow is moving relative to the base of the lamppost. Okay, now we could redraw this and set it all up all over again, but the reality is we could also figure this out pretty quickly because the tip of the shadow is right there, so we really just want the rate of change, or let me put it this way, the variable for that length right there is x plus z. So therefore, what we really want is the derivative with respect to time of x plus z, which is simply dx dt plus dz dt. Well, we already know dx dt. We already know dz dt. So part B, this is part B. So it's 4 plus 4/3, which is 12/3 plus 4/3, which is 16/3 feet per second. Okay, so there's part B. Okay, one more situation here. And this is actually kind of the classic situation for related rates when there's a ladder leaning against a wall. Okay, so ladder leaning against the wall of a house. We're assuming the house is perpendicular to the ground. Okay, the length of the ladder is not changing. And the base of the ladder is pulled away from the wall at a rate of 2 feet per second. Okay, so this length is a variable length. And if it's being pulled away from the wall, that length is increasing. So and I'm going to call that dx, I'm going to call it x. So it's a variable. So dx dt is positive 2 feet per second. Now, if the x is changing, that means the top of the ladder is coming down the wall, so y is also changing. And so kind of looking ahead to that as well. So part A, at what rate is the top of the ladder moving when the base of the ladder is 7 feet from the wall and 15 feet from the wall? Okay. Well, here on part A, what we're really after is we want dy dt at 7 feet when x is 7 feet and also when x is 15 feet. Okay. The y is going to be getting shorter. I anticipate that this is going to be negative, but that's just something that should work out. What's an equation that we can use to relate these? How about the Pythagorean theorem? X squared plus y squared equals 25 squared. Okay, so take the derivative with respect to time. And so we get 2x dx dt plus 2y dy dt equals 0. The 2's, if we multiply the entire equation by 1/2, the 2's can go away. So x dx dt plus y dy dt equals 0. Okay? Now, I believe we have just about all the information we need. So at 7 feet, let's label what's going on here. At x equals 7 feet. So if x is 7 feet, this is a instantaneous measurement. And these numbers are nice. They don't always have to be nice, but these numbers are very nice. So what would the y be? 7 blank 25. Well, y would be 24 at that precise moment in time. Okay, so let's plug in the values we have. So we have 7 times the x dt, which is 2, plus the y, which is 24, times dy dt, which is what we're trying to find out. So dy dt is going to be negative 14 over 24, in other words, negative 7/12. Okay, now, we're doing dy dt, which is a length, feet per second. Okay, now, they also wanted to know at 15 feet per second. So, I don't know, do you think it's going to be the same length, or do you think it's going to be a different length? Let's check it out. Okay, so at x equals 15 feet, well, if x is 15 feet, let's see, 15, 25. Now, this is basically a cousin of a 3, 4, 5. 3 times 5 is 15. 4 times 5 is 20. 5 times 5, so cousin of a 3, 4, 5. So, like I said, really nice numbers. And generally, we try to be pretty nice with numbers because problems are hard enough as it is. So it's still the same formula, the x dx dt plus y dy dt equals 0. So 15 times the dx dt, which is still the 2 feet per second, plus the y, which is 20 now, times dy dt equals 0. So dy dt is negative 30 over 20, which is negative 3/2 feet per second. Okay, now it's not moving at the same rate when x is 15. In fact, if we look at it, we can see that the top of the ladder is coming down faster. I mean, if they were asking for faster, you would just do the positive values of these. But it said the rate, so the negative, y is getting shorter, so it's negative. And so as the base of the ladder comes further away from the wall, the top of the ladder is coming down faster. Okay, part B. Now, I know these notes are long, but really it's like these are notes for 2 objectives on the same topic. So just consider these 2 sets of notes. Okay, so the part B, find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. Okay, so the angle that we're talking about here is right here. Well, let's call it theta. Now, when we are doing angle stuff, you got to involve trig. You have to involve trig. Okay, so now we could talk about sine, cosine, or tangent. You could do other angles. I would just keep it pretty basic. Now, what I do suggest, I mean, yes, you could do tangent of theta is equal to x over y, but then you have 2 variables involved. Why not just keep it to 1 variable for your trig function if possible, because theta is a variable as well. So I would either do sine theta is x over 25 or cosine theta is y over 25. And I'm doing the problem, so I'm going to do sine theta. Okay, so here's part B. Sine theta is x over 25. Okay, so there it is. I want d theta dt. So I'm going to take the derivative of both sides with respect to time. Okay, and so the derivative of sine is cosine of the angle. The angle does not change, times the derivative of the guts with respect to time. D theta dt equals. Okay, now this is 1/25 x. So the derivative is going to be 1/25 times dx dt. Okay, now, we know dx dt. We are given dx dt. Dx dt is the positive 2 feet per second. And d theta dt is what we're trying to find. Okay, so we have 1/25 times 2, and d theta dt is what we're trying to find. Okay, now we're doing this, what did it say? It said at 7 feet. Okay, so does that mean we need to actually calculate the angle? No, you don't need the angle. We need the cosine of the angle. So let's remind ourselves what the cosine is at that precise moment in time. When x is 7, the y is 24. And so the cosine of theta at the precise moment in time is 24/25. And so 24/25. And now I just solve for d theta dt. Okay, so d theta dt is 2/25 times, okay, multiplied by the reciprocal, 25/24. And we can see that we get 1/12. Okay, now it's an angle. What are units for an angle? Well, first off, what's an angle measured in calculus? Radians. Radians per second. Okay, radians per second. Okay, finally, part C. Part C, we've got at what rate is, consider the triangle formed by the wall of the house, the ground, and the ladder. Okay, yeah, there's a triangle there, obviously. At what rate is the area of the triangle changing? Okay, area of the triangle. They want dA dt, so we need an area formula. Well, that would be 1/2 base times height, 1/2 xy. When the ladder, base of the ladder is 7 feet from the wall and 15 feet from the wall. Okay, so part C, dA dt, which means I need area. Area is 1/2 base times height, 1/2 xy. So if I take the derivative of that with respect to time, we get dA dt equals 1/2. And I just like to bring the 1/2 out in front. And then I've got a product of variables. I've got to do the product rule. First times the derivative of the second with respect to time plus the second times the derivative of the first with respect to time. Okay, now we know dx dt, because that was given to us. Do we know dy dt? Well, yeah, we do, because remember part A, we calculated at different values here. Part A, we calculated at x equals 7 feet, and we got dy dt at 7 feet. We got dy dt to be negative 7/12. And then we're also supposed to be doing this at 15 feet. And so dx dt, sorry, not dx dt, that's not the one we want. The dy dt there was negative 3/2 feet per second. Okay, And let's also write down what the y values were. X was 7 feet, y was 24 feet, and when x was 15 feet, y was 20 feet. Okay, so really we're just plugging all those values in right now. So dA dt, okay, is 1/2 times, okay, x is 7, dy dt is -7/12 plus the y, which was 24, and the dx dt is 2. Okay, now the notes are going kind of long here, so I'm just going to tell you that that this turns out to be 527 over 24, and its area, so square feet per second. Okay. Now, if we go through and if we do it for the 15 feet as well, we're still plugging in the same formula. If we do all that, we get dA dt, okay, is I have it here somewhere, sorry. I've got it, okay. 35 over 4, sorry. 35 over 4 square feet per second. Now, these are rates. So notice that as they're both positive, so the rate of change, the area is getting bigger as the top of the ladder is coming down. Now, does that mean that it's going to keep getting bigger all the way until as the top of the ladder keeps coming down the wall? No. In fact, if you notice, the rate of change of the area is actually bigger when the y is further up, and it's not as big, even though it's still positive, as the y value is a little bit lower. We did max-min stuff recently, and the largest this area of the triangle will ever get is when it's like a 45, 45, 90 right triangle, and as soon as the top of the ladder gets down below where it's a 45, 45, 90 right triangle, the rate of change of the area is actually going to start getting negative, because now the area would actually be getting smaller. So anyway, some things to think about. And yes, long set of notes, sorry, but it's all really good stuff.